Good afternoon, everyone, and welcome to our second day of AI training with AMD. I'm Sima, Work Package 3 leader of CASTIEL 2 project, and I'm delighted to open this session. I would like to thank our organizers, NCC France, as part of EuroCC 2 project, AMD team, and also CASTIEL to my colleagues, Velasta and Maxim. I see that they are here. So today will be advanced course. So the focus of today will be Python tools. Our AMD expert teams are today dear Bob, Giacomo, and Jose. And now I'm giving the floor to our AMD team to introduce themselves and kick off the advanced session. Thank you very much and enjoy.
Welcome, everyone. Today we're going to be mostly talking about the Python tools. There's quite a few tools available, but often the information on them is difficult to find. So first recap from yesterday, we talked a lot about the different AI packages that you could run and different ways of running them. And the AMD Accelerator Cloud is available for you to continue to try those exercises as you have time to look at them. Today, we're going to start out with HipPython and then move on through CuPy, MPI4Py, and then we'll finish with the AI Assistant creation, how to create your own AI assistant. So let's go. I'll start sharing here. If you have questions, please post them in the channels as Marie recommended. And we are focusing on getting the SSH keys working for those who registered last week. We have not had time to add any more. It took most of the weekend to get the ones we have on the system. So that we'll do after we take care of all the ones that registered last week. Okay. You want to add anything, Giacomo, while I'm starting the share?
No, just saying hi, everybody. Good to see you again. Big thanks to all the organizers for kicking this off and being great at providing us with all the tools. We're very grateful for that. And yeah, I'm excited for second day of fun.
Try to upload the PDFs for the presentations today. My firewall was telling me I was not allowed to upload them, so we're trying other ways to get them there. So HipPython has been around for a while, but there's not a lot of information on the AMD site or elsewhere, so we're going to start going over it here. So HipPython is basically a Python wrapper layer to access many of the HIP libraries, software, and it also provides Python and Numba or a gateway to Numba. So there's many options here to further speed up your Python code. And some of the libraries that you might be interested in reaching from HipPython are HipLaws, HipFFT, the solvers, RCCL, and we'll have examples of some of those. So it basically creates a Python wrapper layer over those C libraries. It is interoperable with CuPy and Numba. So those will, you can use them interchangeably. So you can exchange the buffers. And On the MI300A, you can take advantage of the single address space, which is actually pretty cool. It makes it a lot easier. So we have a couple exercises that demonstrate that as well. So there's a bunch of different links that you can download from the Python server. And the 7.0 versions, I got word they have been uploaded in the last couple days. So we're continuing to see that the various teams at AMD are shortening the time to release products for the latest ROCm release, and sometimes almost immediately. So there's also a HIP Python fork on the main Python server. The official one is still on the test Python server, and somebody has forked it and moved it over. I do want to warn that there is another package called HIP Python that's not related on the main server. And I think they're trying to figure out what to do with that, how to rename things or how to post the HIP Python. So the way you install it is with this pip install command, and you have to point it towards the test server. And you'll see this squiggle equals to say approximately 6.4.0. So we have it installed on the system in a module to make it easier for you to do the exercises. You can download it if you're on your own system directly. So the HIP Python examples, we have several of them here. So we're going to really walk through the capabilities of HIP Python by going through the exercises and demonstrating it. It's typical Python code. It's the enabling of the HIP that is special about the package. And this is used to enable a lot of other Python. Each of the HIP Python routines returns an error code, which you can check with this short section of code. I am not going to include those on the slides. The hands-on exercises have the error checks in the code, so you'll see it a little more verbose as you work through the hands-on exercises sheet. So if you're following along on that and trying the exercises, you can jump to that section and go ahead and log on to the AMD cloud and try these exercises. They're fairly simple to run. And if you need the more debugging out of what's going on, you can set this AMD log level during the run. That can be helpful to see what's going on. So getting device properties, this is actually kind of impressive that they have you can retrieve all these properties of the GPU you're on. So you can get the warp size, the block and grid dimensions, and this code, the device properties will print out a bunch of the different properties you can get, and then the get attributes will show a selected set of the attributes that you might be interested in. So by querying this, you can make a decision based on what GPU you're on of what you might want to do in the next section of code. So once you know what type of GPU you're on, you can go ahead and do things like create streams in HIP. So we talk about being able to create multiple streams that can operate at the same time. In this example, they're only going to it only creates one stream, but you could create multiple streams and operate on them in an asynchronous fashion. So this is showing creating this stream and then how to pass data to it asynchronously back and forth, and synchronize and then destroy the stream. So you can see you can reach the base HIP functionality directly from Python. And then calling HIP laws using HIP Python, you can create your arrays using NumPy here. So these are NumPy arrays, and we're going to fill them with random numbers. And then we can first calculate our expected results, and then do a HIP malloc, so we've got memory on the GPU, mem copy to the GPU, and then do the BLAS calls. So we have to create the BLAS handle, run the Saxby, and then destroy the handle. Copy the memory back. Now, there's a lot of memory movement in here, and much of this can be skipped if you're on an MI300 GPU. So look at the exercises. There's an exercise showing doing the same operation on an MI300A. And so here's the source code for that version. So you notice here we just create the arrays on the host, and we can directly use that in the BLAS call. So it makes it much simpler on the using that APU programming model on the MI300A, or on our discrete GPUs with the managed memory. So this shortens the code by about half. So it's it maybe even more than half. So this is a tremendous simplification of writing code based on using that capability of that APU programming model. Okay, the next one. So we've seen how we can call a BLAS function, and BLAS functions that can be very useful, but one of the other really common routines to call is FFTs. And so you can create your FFT plan. This is showing the discrete memory movement. So we're allocating the memory and copying it. And then we're going to copy the memory back and destroy our plan. Now you can already start looking at this and saying, what can I eliminate if I were to do this with managed memory in the APU programming model? And you can see there's a lot of lines we can eliminate on the MI300A. And this is showing that simplified code. So we can create those arrays and directly call the HIP FFT with our host pointers. You may be doing RCCL calls from Python, and here you can call the RCCL, and you see it's RCCL.NICL. As happens all too often, some of the CUDA nomenclature still comes through. And so we're going to initialize the communicators, and then initialize the data on the device, and then we can call the broadcast function. And here we've got that group start and group end to activate the communication, and then we can do a COM destroy. So all of those RCCL functions can be called directly from Python. There's a few tricks in here. Since Python sort of automatically detects types, you'll notice this comment in here that you have to tell Python that this should be treated as an int instead of an array buffer. So again, unified shared memory on the MI300A, or if we're emulating that, on the discrete GPUs, we can eliminate a lot of the allocations on the GPU and use the CPU handles directly. This is a little bit more complicated than the previous examples on how to use the host data type. And so we're doing the check, the cleanup, and then doing the destroy function. So all of these are exercises in the handout. We move on to a different kind of capability. If you are running Python code, and let's say you're running some sort of AI package, and you need to stage data for that PyTorch or TensorFlow or JAX model, and the acceleration on the GPU is very fast, but you still have some Python code which is which is really causing the bottleneck in your performance. Well, we can actually compile the Python code using Cython. And so we take this array that we want to compile and we put it in a file with the extension .pyx, and then we define an interface to it. And this is a very simple example. You could include hip calls in here as well. And so then we're going to import Cythonize and compile the code. So we have to get our ROCm path to support that. And then in the setup call down here, we're going to Cythonize. That's a verb, it looks like. Cythonize the code. So we basically compiled it, and this will speed up the code. So that's an option that you can use if you've got something that's causing a bottleneck in your application. So how do we run the Cython? Here, this is using a virtual environment to run that Cython example. And you can load, I think this is wrong. This is module load ROCm, and it's probably hip-python. I think we have a autocorrect here. So we want to load the hip Python module and then import Cython, compile the Python code, and now we have a virtual environment we can use. There are a lot of details on Python data types that help enable these routines. I did not put a lot of detail in here because it gets a little too deep for a overview presentation. But there are pointer types that'll map the objects to C pointers. Types that will handle the return of hip malloc and memory allocation, and then some list types for the return from various or input to various routines. So as you get into more complex Python code, these details may be important. Okay, so moving on to another way to compile code, we can use Numba. So Numba hip can be used to compile some functions, and it's installed on our system here as in the hip Python module. And so you can experiment with it and install it. Here's how you would install it in a virtual environment on your system, and then how to clean up afterwards. Notice that the pip install command is a little more complicated here. And we're also still using the test Python repository and telling it we want the major ROCm release number that we have on our system. And they should have the 7.0 up here as well. So here's an example of a Numba code. So from Numba, we're going to import HIP, and then we can use those HIP functions, hip.grid shown here, but we can basically write a kernel this way. So we can directly build a kernel to run on the GPU. And then we can run this example, so you might try that one out. We can also, if we have a code that is written for CUDA HIP, we can use this simple call to translate all those calls on the fly. And so we can basically have a Numba HIP pose as a CUDA Numba routine. And so here we're going to do a CUDA JIT. I think this is right, hip.grid. I believe it's in the example, so that must be right. But we can do a CUDA JIT instead of a hip JIT. And so this will compile that routine without making major changes through your code. And that may be more portable for some of your applications. I did not include details on the HIP Python. It also has a CUDA interface that will allow you to incrementally port to HIP Python. And that concludes that presentation. Okay, so that's our first presentation for the day, and I believe we have some exercises for about 20 minutes to run through each of these and let you see what problems you encounter and ask questions.
And please, if there's anyone else that doesn't have access to the clusters, ping us on Discord and we'll make sure that you can get in.
Okay, what happened to my Discord?
By the way, nice presentation, Bob. That was the first time ever you showed that presentation.
Yeah.
So a lot of first times.
Yeah,
in this event.
we did a port of a DNS solver to Python, trying to get it running on the GPU a few years ago at LANL, and found, information on the how to do that in Python was just really, really scarce, and it's only gotten a little bit better over the last few years. So these kind of details can really matter. I think we just could not get the performance to work to really be useful because it was doing data conversions when we were sending it to MPI for Pi. And so I hope there's enough information here to help people on writing HPC applications as well as AI applications. Okay. Do we have any questions? Do we expect it to work better? Yeah, there's been a lot more work on Python in taking care of some of the details and adding things like GPU aware MPI handles into the library so you don't get these conversions on the host. So I think things have improved, but what I really would like is some more detailed examples here. If you've got maybe some not full applications, but something that's doing a little more complex operations in Python, I think it would help the whole community on how to do these things. This is still pretty simple examples. Okay. Giacomo, were you able to upload files?
Seema was, yeah. I asked her and I sent her the slides and she kindly uploaded them for us.
Yeah, it's not permissions in Discord that are the problem. I get my VPN starts popping up messages saying you're not allowed to upload files. I don't know why today. It's kind of weird.
Happened to me as well, yeah. We must have gotten some AMD software firewall update last time. There's a comment in the chat from Ashwin. So Numba heap was news to me. Yeah, so it was news to us as well up until 1 month ago, honestly. We kind of had to dig for it because we were looking for content that was Python relevant to show you all. And this came up after we asked around. And I think some of these packages, like Python, came up as like byproducts, pass me the term, of other efforts. But then we thought that it was interesting to bring them up to y'all's attention. And we talked with other people that were also excited about Numba Hip.
Yeah, and our developers actually were very excited that we were going to present on this. Dominic helped us out with the Hip Python, and Grant helped out with the CuPy. We also got some help from the Rickle team and from our MPI gurus on MPI for Pi. So um, they would like to see more activity and questions from the community. I think it would encourage them to get more material out there and work more on the packages.
And Bob, since we're here, do you want to spend 5 minutes talking about the university program?
Yeah, so the yesterday Giacomo showed some slides on using the AI assistant, and some of those slides on how to build prompts were from some of our colleagues, but also from something called the AMD University program. And the AMD University program, it engages a lot of universities for education and also for university grants. So we have a couple projects, one in genomics that we have a university student working on adding some GPU capability there. So that's a very useful program if you're looking for more academic and maybe graduate student opportunities. Do you want to add anything more about that?
Yeah, and I think that they're still able to provide access to their cluster for university folks that are interested in testing out. And they used to have some hardware that was not the latest, but I think they are getting some 300s recently. They were getting some
They have
300s
some
recently.
300Xs. They don't,
Yeah.
I don't think they have 300As. Um, uh, and yeah, they have, you can get some time on their machine if you're an academic institution. And they're actually also do FPGA education. So they have a very active group across the whole spectrum of compute hardware.
And some of them are in Europe. So I think they recently had an event in Europe. So they're active there.
See, do we have a exercise handout I can pop up? Let's see. I thought I downloaded those. Let's go ahead and look at where the exercises are. And the same exercise document is for all 4 days. And there will be mistakes in the exercises. We tried to clean up some of the formatting, but there's 200 pages. It's actually a little mind-boggling to catch all the problems there. We do have in our examples, we have 300 tests we run through to try to catch problems with some of our exercises so we don't run into them during the workshop. So here's the CASTIEL AI exercises document. And if we go down to the bottom of the first page on the PDF, you can click on Hip Python, and it tells you the README that it comes from. And this can be helpful if it cuts off lines on the right because they're too long. Some of the lines don't wrap properly in LaTeX. And So you can step through these examples. You can see the device properties here, attributes, the HIP stream, and the source code for this is in the examples directory or repository under Python, HIP Python. So you don't have to type or copy these in. You can just run them directly. So all the examples, and I think there's a couple extras in here that I did not put in the slides. We try to put extra ones in if we have them. You can't present all the examples in just 30 minutes. So take a look at that and get more familiar with what you can do in Python and actually drive the GPUs with it. Okay, so I think we're a little bit ahead of schedule still.
Do you wanna take a look at that question that we've got on Discord about one of the examples?
Okay.
I think if you're working on our cluster, Ashwin, there should be a module so you wouldn't have to install it unless you're just trying yourself. And we have a script to install so we can compare what you're running with what we have in the script.
Okay. Yeah, I had a little trouble doing the pip install here. Yeah. Did you do the line before it to set the environment variable? And yeah, I'm not quite sure. I know I struggled a little bit with getting this to download properly, but it is in the module. The other thing that would be useful, Giacomo, is popping up the training doc page for HIP Python install.
I have sent them the link. Hold on. Is it coming through?
Yeah, here we go.
Let me go down to the relevant part.
So when we install a module, we record all the instructions and build this install file. It's partly for ourselves as well because we don't want to figure it out again. So you have to set this global extra index URL. This is so the line above that on 105, you have to set a configuration to pull it from that test Python package repository. And then I did get it to work. So see if that helps it or if we have some other issue. And you notice because on especially on Ubuntu 24.04, it doesn't let you do pip installs as root, so you have to put it in a virtual environment and then install from that. Let me check the system, see what our workload is there. Okay, we got pretty good usage on the system right now, but there is one of the PeriPeak air-cooled nodes. Well, it looks like it may be fairly full right now, so you may have to wait for the srun to run. If you are having that problem, the SH5 nodes are completely idle, so you can add that instruction to I'll put it in the Discord. And the SH5 nodes are fine for this kind of work.
There's a question about libraries with HipPython. Is there any example where HipPython libraries are used or could be used to get optimization while running CNN with PyTorch?
You know, just looking through the Python package repository, there's thousands of packages there. Some I'd never heard of. Some of them with HIP capabilities in them. So maybe I just don't know about them. It's hard to keep track of the Python libraries, but that would be interesting. We have a collaborator at San Diego Supercomputing that is trying to get some of the Python packages for fluid dynamics working. and for some of the biomedical applications. And there's a whole bunch of stuff out there, but very little information on it. This would be maybe something to try and grab that information and put it in the AI assistant so that you had a way to search it and grab the right ones. This note that you do have to do a pip upgrade. I remember now that we had to do that. And I don't know, is that in our install script, Giacomo?
Let me check.
Did I do that in the pip in the virtual environment? This is one of the problems with Python is I might have done it for my system or local pip command and not realize that I needed to do it in the install as well in the virtual environment.
Looks like it's not in the script.
Yeah, so maybe I need to add that.
Yeah.
We might want to test it I actually want to wipe out my local directory and the system directory and try these things because you can get surprised. So all of the materials that we have uploaded for the slides, for the PDFs, and the exercises, all of those are open source. All the installation recipes are in an open source repository. The examples are all open source, MIT license. If you do use them, proper attribution, where you got it from, and please don't attribute negative comments about other vendors related to that, because if it looks like it's coming from us, we get some nasty messages sent our way. Okay, and all the slides and the handouts are in the guides channel. I have a couple fixes to the exercises I will post later in the next couple of days. They're small enough, they're not worth doing yet. Okay, so do you want to go ahead and start the CuPy? And
yeah, let me just find the slides. Okay. And Bob, there's a question in the Discord channel.
okay.
If you want to say something about it, it's more of an HPC related question, but pull it out. Yeah, Francois is asking, what happens if you use a piece of heap code that has explicit memory management on an MI300A?
Okay, got a couple questions here. Yeah. So, Giacomo, is that I'm sure I'm not pronouncing that right.
Oh,
Did
sorry,
you
it's Francois. So it's the, if you look on the Q&A, scroll all the way to the bottom. I responded to him on the chat. You can go up and see what he asked.
Okay, Francois.
Yeah, so I think that because we're doing a lot of Python, we're not spending probably enough time with our usual spiel on HSAX NAC and setting it to 1. So maybe we should make a couple of comments on that.
Yeah, there's a short note in the hip Python that you need to set that, and on some sites they're actually setting that as the default, and we tried that. You can set that in the Bash RC or other places and make it default. We had a couple small issues with it, so we still have it setting that you have to set it by hand. And if you have explicit memory, it still works. And there's two things that may happen with explicit memory. You may end up with two copies because you're doing a host copy and a device copy and copying between them on the MI300A. That will be very fast, but you're cutting your memory basically in half by doing that. And so a single address will have some benefits there, but it will run explicit memory code. Yeah. And it is pretty awesome when you look at how much it simplifies the code. And it's the parts of the code that you're going to get wrong too. I think the number one error in GPU programming is mixing up the host and the device pointers, which one you're providing to the call. There's also a little note that if you provide the device pointer, it's going to do GPU aware MPI. If it's the host pointer, it's going to do the CPU MPI. So when you do the MI300A, which does it use? And it depends on what you allocated with. So if you do a HIP malloc, it will use the GPU aware MPI. And one of the things I want to add to our presentation is how to verify that, because it's confusing.
Yeah.
Yeah. So the HSA-XNAC fixed that. Yeah.
And yeah, I sent Francois in the chat, and I mean, I think other people can see it, that little example that we have on the repo with the different allocators with HIP, and see how that changes the runtime for a kernel. On 300A, ideally, all the allocators will work the same. But as Bob said, we suggest to use HipMalloc because then you get all the benefits of using that for MPI and GPU or MPI specifically.
Yeah, and
Okay.
let's go ahead and move on to CuPy. It's got some similar capabilities, but there's some unique things with HipPython that are actually worth being aware of, even if you're using CuPy. But let's look at CuPy because it's kind of neat.
Okay. So yesterday we have shown a brief overview of what are the frameworks and the packages that support running on AMD GPUs, and CuPy was one of them. So we have briefly talked about CuPy yesterday. Today, we're gonna go in more detail about what you can do with CuPy, how it interfaces with NumPy and SciPy, and also we'll discuss AMD's effort into bringing up to the upstream repo the latest feature integrations for CuPy. Okay, so a brief recap for those of you that were not in attendance yesterday. So CuPy is basically a NumPy / SciPy compatible array library that will let you leverage the GPU when you are using your Python code. So even though it sounds like an NVIDIA product, because of its name, is actually not an NVIDIA product. And it can act as a drop-in replacement for your existing NumPy and or SciPy code. And it will work on NVIDIA, but also AMD ROCm platforms. And CuPy has the ND array structure that stands for n-dimensional array, just as NumPy does, but it also handles sparse matrices, and it interfaces as well with some of the ROCm math libraries such as ROCblast, ROCsparse, ROCFFT, and also the communication library that's RICO. One advantage of CuPy is that most of the API is the same as NumPy and SciPy, so you don't have to worry about you know, the right syntax when you want to leverage CuPy on your NumPy and SciPy applications. Okay, so I'm going to spend some time talking about CuPy and HIP. So Bob has talked about HIP Python already, and I want to make a comment. Obviously, HIP Python, by its name, clearly it's using HIP, And we talked about HIP yesterday a little bit, but for those of you that were not in attendance, HIP stands for Heterogeneous Compute Interface for Portability, and it's a C++ runtime API and kernel language from AMD that basically is used as a low-level programming language to communicate with your GPU. And it's portable in the sense that if you use HIP for your programming, then your code will run on both AMD and NVIDIA GPUs. So most of these Python packages that leverage ROCm to run on GPU use HIP as backhand when you run on GPU. And obviously HIP Python does, but so does CuPy and so does PyTorch, for instance. So because of this fact, because of the fact that the backend is HIP, CuPy inherits some properties of how host and device work when you are programming with HIP. So by host, we refer to the CPU, and by device, we refer to the GPU. So when you program with HIP and you launch a kernel that executes on the GPU, that kernel launch is non-blocking for the host, which means that after you pass the line on your code where you launch the kernel, the host will continue the execution of your program and will proceed with just doing something else. So as your kernel runs on the GPU, the host will keep, doing something else. So you have to be careful in that case because you may incur into race conditions where you're trying to access the data that supposedly is already been worked on by the GPU, but maybe it's not. And so you have to put synchronization barriers that synchronize the host and the device after the kernel so that you can make sure that when you operate on the data, it is where you think it is. And you have to do that with HIP, but since CuPy leverages the HIP backend, you also have to do it with CuPy. So to do that, you'll have to use this syntax here, CuPy.CUDA.device, and then you specify the specific device you want to synchronize the host with, and then .synchronize. So as we've seen with PyTorch yesterday, the syntax is to do a .CUDA, so you're not going to have .hip or .ROCm, but it will still work on our AMD GPUs. And then Bob mentioned streams in his presentation. You can also do a synchronization with a specific stream. So the first synchronization is a hard stop where basically the host stops any activity until all work on the GPU has completed. Whereas if you have enqueued your GPU activity that could be kernel launches or copies, for instance, on a specific stream, then the synchronization with the stream will have the host wait only until the work on that specific stream has been completed. So it's an easier stop. It's a stop that has less constraints than the one where you stop everything with the device synchronize. So it's also important to mention that in HIP, memory copies are blocking for the host. So if you do a memory copy, say from host to device or vice versa, then that already has a synchronization point. So for instance, if you have your HIP code that runs on a discrete GPU where you have a kernel launch followed by a mem copy, and then you port that to 300A where you have the unified shared memory framework, you could technically remove that mem copy but you would have to swap that with a synchronization because that would be implicit in the mem copy. So because the mem copy is blocking for the host with HIP, it will also be for CuPy since it's leveraging the HIP backhand. So you don't need to put any synchronization call after a mem copy. Okay, so now that we have gotten this out of our system, we can continue talking about Python specifically. So you've seen this slide already yesterday if you were sitting in the meeting. So these two screenshots here are meant to show you that the NumPy API is indeed very similar to the CuPy API. In fact, you see that other than having NumPy dot that you would replace with CuPy dot, most functions are indeed the same. And anything that's specific to CuPy will be under the CuPyX namespace, like what you're seeing here in this slide. And if you click on this link here, there's going to be more details about what are the differences between CuPy and NumPy. Okay, so now let's spend some time talking about how to install CuPy and where to actually get it from. So for our discussion here, there's going to be two GitHub repos that are relevant and that will allow you to run on our GPUs. So there's the upstream CuPy repo, which is just on GitHub, CuPy/CuPy. And then there is the Rockham fork, which is Rockham/CuPy. So both of these work if you want to install CuPy. However, there actually is a lot of work ongoing on our side to push upstream the latest features for Rockham support on CuPy. And in fact, you'll see that the Rockham fork of CuPy is actually pretty old at the moment in terms of tags. So the latest tag is from 2023. And that is because the latest stuff is soon to be included in that Rockham fork. So there's work on our side to have that pushed upstream and also to our fork. So that's why the fork looks old in terms of the latest tag. So for what you have on the cluster, we have used the upstream repo for which the tag that we used is just from August 18th. And this slide and the next one, these screenshots have been taken on September 23rd. So see here, the next slide, this is from the upstream repo. This is a screenshot to show you that there is indeed a lot of work that's been done. So G. Pinkert is Grant Pinkert from our company, from AMD, who is the person in charge of working on CuPy. And you see that he has worked quite a lot on including features for Rockham support on the upstream repo. And he's still working on it. If you check out the CuPy PyPy page, if you're interested in getting a wheel, and you know from yesterday that wheels are the pre-built packages that you can install with just pip install. The pre-built packages for CuPy that have Rockham support are super old. They're like Ice Age old, because those are for Rockham 5 and now we're at Rockham 702. And yeah, I don't want to even mention Rockham 4.3. That's just way too old. But new wheels are coming for Rockham 6.4 and Rockham 7. So stay tuned because they will appear on this page hopefully very soon. Okay, so for what concerns the installation, there's some instructions on the CuPy documentation on how to install CuPy. And basically what I'm showing you here is from the docs, and it's actually pretty simple. You just have to make sure that you export these 4 environment variables. So you have to basically tell CuPy that the installation will need to use HIP. You have to have ROCm installed and then point to the ROCm path, which if you load the ROCm module in our systems, that will be already set for you. You have to set an environment variable for the HipCC compiler, and then you have to specify the architecture. So for 300A, this AMD GPU GFX model will be GFX 942, for instance. And then you would do this pip install. So just notice that even though you're doing pip install, this is actually an installation from source. So be aware of that. And if you don't specify the architecture, then it will be built, CuPy will be built for the architectures that are available on the system. So if you're trying to cross-compile, if you're trying to build on a system that doesn't have your target GPU and then deploy that install where you actually have it, make sure to specify this flag. And as Bob said, with Ubuntu 24.04, there are some restrictions on installing with just pip install. You'll get errors that look like that. So we take that into account in our installation script, where we basically do what the docs are suggesting, but we also set that installation into a virtual environment to have that working also with Ubuntu 24.04. And notice that we're also installing a bunch of other stuff, such as PyTest, mock, and then we're also installing Xarray and CuPy Xarray that will be talked about later in this presentation, as well as NumPy allocator, which we'll discuss in a second when we actually talk about how to use unified shared memory with CuPy. Notice that when we do the pip install, we also specify the target where we want the install to happen. And if you were here yesterday, you heard me rant about how I think that it's always very important to specify the target location for your install, because otherwise, if you just do the blind pip install, then you'll have a million packages in the same place with conflicting versions, and it's gonna be a bit of a nightmare. So make sure to, this is just my personal opinion, make sure to always, compartmentalize your pip installs and just put your installation on the specific path that it needs to be in. Yeah, so this is our script at our usual training.repo repo if you want to give that a try. And I think we said it yesterday, but I'm going to say it again. Our scripts are intended to both work with sudo and without, because we use them inside Docker containers. But you can also just specify a location in your home, for instance, and the scripts will detect that and basically not use sudo. So you can use them just as a user and install in your home. Okay, so after this introduction, let's actually get down to business and talk details about how CuPy works. So obviously you have to import the Python module with just the usual import CuPy. And then you can create an array that exists on the GPU just by using cp.array. And then if you have an array that you have created with NumPy, basically, that will create an array on the GPU. So this would be your mem copy, basically. This would be the mem copy from host to device. And then you can move back from GPU to CPU with this as NumPy, and then back from CPU to GPU with this as array. Then when you have your GPU arrays that exist on the GPU, if you do operations on them, those will happen on the GPU. And then CuPy has this concept of a current device that you can query with the dot and then device, and it's usually device 0. And if you print information from that operation, you'll see something that looks like this. So CUDA device 0. So it still talks about CUDA, but that actually is an AMD GPU if you're running on our GPUs. Okay, so let's spend 2 minutes talking about the interoperability between NumPy and CuPy, because it's very important in this context. So we said that CuPy implements the ND array, which is basically the GPU counterpart of NumPy ND arrays, but it also implements within that the array ufunc interface, and that allows basically NumPy universal functions to be applied to CuPy arrays. So what does that mean? If you look at this snippet of code for Python, we import CuPy and NumPy, then we initialize some random array using CuPy on the GPU, because we're using CuPy. And then notice that we are passing that array to a NumPy function. So this is numpy.sum. We are passing that to NumPy. And if we print the type of the result, this is still a CuPy array. So this code snippet here is meant to show you that you can pass CuPy arrays to the universal functions for NumPy, and also the type is consistent with your input even after that operation. CuPy and the array also implements the array function interface that basically allows you to define an array with NumPy, move that to the GPU, and then feed that to an algorithm that is implemented in NumPy, so this QR factorization, and that will still be on the GPU as output. Okay, so you have something on the GPU, you feed it to NumPy, and it's still on the GPU as the result. So this simplifies a lot the way you use CuPy in your code. But then I'm sure you are wondering, well, which one do I use? Do I favor the NumPy calls, or what is the best way? Well, so there's some examples that I'm gonna show you next where they're trying to answer this question, and in general we've seen that the performance is similar, but I'm gonna let you decide which one is best for your case. So if you go on our training examples repo, there's a subdirectory called Python, where among other things, there's one directory for CuPy. So there's a simple array sum there example that you can run. You'll have to load the CuPy module with just doing module load CuPy. And notice that this is not the Python module. This is the module in the HPC sense. Basically, when you do module load CuPy in our system, you are just setting the Python path to the CuPy installation, so that when you import CuPy in Python, it's found. So module load CuPy, and then you can run the example just by using Python, and the output should look like that. So this is a very simple example where we have a CuPy array, so that exists on the GPU. We are squaring it, and then we're doing some mem copies. So let's take a look at that in a little bit more detail. So this is how the Python code looks like, we are importing the Python modules for CuPy and NumPy. So now this import is actually the import of the Python module. We are creating an array on the GPU here, and then we're just printing it. Then we are doing this squaring operation on the GPU. So once you have that array, as we said already, if you operate on it like this, for instance, we've seen the sum before, and now we're doing the power, that will be still on the GPU. We then create a NumPy array on the CPU, and we do the transfer from the CPU to the GPU with as array. And then you see that now we are doing a sum once again with the initial array and then the one that we copied. And then we copy back the result back on the CPU. Okay, so yeah, so this is showing you the copy from CPU to GPU with the CP as array, and then from the GPU back to the CPU with as NumPy. So these two are the two mem copies that correspond to the heap mem copies. Basically, these are the mem copies that use the heap mem copy under the hood. Okay, and the next thing is to actually check that you are running on the GPU, because unless you explicitly check that, it may not be obvious. So because we are using the heap backhand, we are going to export this environment variable called AMD log level, and depending on the number you assign to it, you'll get more output. The larger the number, the more output you get. But this is gonna print the heap activity in the backhand as you execute your Python code. So if you see that activity, such as here, you see it's showing the mem copies that happened under the hood, the synchronization. So if you see all of this, then it means, yes, you are running on the GPU. Okay, so now, since on this event, you actually have access to MI300As that have the unified addressing, it's worth actually trying some CuPy code on these machines. Here, this screenshot here on the left is taken from the CuPy documentation. I'll give you that the experimental with boldface and exclamation mark is probably not super reassuring, but we tested it out, and it seems like it is indeed working quite well. So basically, this framework here lets you leverage the unified shared memory that exists physically on MI300A with CuPy. And you can still do this unified memory programming with CuPy on a discrete GPU. You can still do that, but on the 300A, that's where you're expected to see the actual benefits of doing that. So to enable it, you'll need to install NumPy allocator, and now you see why we included that in our script. You also need to set this environment variable for CuPy, so CuPy enable UMP. But now you know that if you're running on AMD GPUs and you want to leverage unified shared memory, additionally, and this is specific to AMD, you'll also have to export HSA XNAC and set it to 1. Yeah, so then you have to include these lines of code in your Python code, where basically you are making a memory pool for CuPy, and then you are switching to the aligned allocator for NumPy when you so that you can draw system memory. So after you've done that, basically there's nothing else you need to do. And the effect is that the data movement with as NumPy and as array, as we've seen now, becomes a no-op basically. So there's no copy happening when you move the memory from CPU to GPU and back. And there's an example that you can test out in our examples repo. It's once again in the Python subdirectory and then CuPy. And this is basically a little benchmark that compares the timing of some of the operations that are relevant to this case with and without the UMP framework for CuPy. So you would run it with just Python 3 and then CuPy umpbench.py, but we first suggest that you test it with a -- help so you can see what type of input flags you can provide. For instance, you could provide the size of the arrays that are tested for copies, or the number of warm-up iterations before you measure, or how many times you run the operations for the measurement. So what is checked in the benchmark are the host to device copies. So with as array, device to host with the get. So for device to host, we've seen the as NumPy, but you can also do a dot get. And then it's added into arrays on the device. And then there's the last one, which is basically a mix of all these. So you copy to the GPU, you add on the GPU, and then you copy back. So these are the four workflows, let's say, that it's testing. So when you actually run it, this is what it looks like. I tested it on one of our workshop nodes. So this PeriPeak PL1 S24-26. So you can actually reproduce exactly what it did and see if you get the same numbers. Well, you probably get different numbers, but that's expected to some extent. And so see that what you get here, it's measuring both the time in milliseconds as well as the bandwidth here. So you see that with comparing the base, so the base is without leveraging the unified share memory, and the UMP is with unified share memory. You are getting basically a lot faster on the host to device. And then here, device to host is somewhat comparable in terms of time and bandwidth, and the same happens with the pipeline and the ad. And there's additional examples that you can check out. These are from a recent tutorial that was given at ICPP in San Diego that we worked on delivering with the San Diego Supercomputing Center. They are actually the ones that delivered it on site. We worked with them on the material. And Igor Sviligoy has some of the examples that he has shown during the tutorial on his GitHub page. And I recommend you check them out because he shows also what I was telling you before. So basically a comparison between NumPy and CuPy on some of the operations on matrices. And he also has some examples with SciPy, for instance, that shows that sometimes the API is not exactly the same, and so you have to do some copies, for instance. And then he has an example where is basically using the unified share memory on one hand and not using it on the other, and he compares some of the numbers. So last but not least, we should talk about CuPy Xarray. So as we said yesterday, Xarray is a Python library that turns out to be very handy in cases where you have to handle labeled multidimensional arrays, which is often the case, for instance, in climate applications and climate codes where there's a lot of data to process. And it's built on top of NumPy and has built-in support for netcdf, which is a format that a lot of folks in that type of environment, scientific environment, use. And obviously, when the data is very big in terms of size, then just using Xarray can become a bottleneck for certain applications. And to make that easier, there's this CuPy Xarray package that provides an interface for using CuPy in Xarray so that you can actually speed up by using the GPU the handling of your data. And to install, you just do the pip install and then CuPy-Xarray. And we like to specify the --no-deps to make sure that, for instance, it's not gonna try to reinstall CuPy for you because we want that to use our installation. Yeah, and you also need to install Desk. There's this open pull request here because Desk didn't make it into the release, so you need to install that. Okay, so we've got an example in the usual directory that I already talked about. It's called CuPy_Xarray_test. And basically, once you run it, it'll show you this output here. So let's go and take a look at that little code real quick. So once again, we're gonna import CuPy and NumPy as Python modules. We're also gonna import Xarray and CuPy-Xarray. The latter adds the .CuPy to the Xarray object, so that's why we need it. So we're gonna create some random arrays on the CPU with NumPy and then on the GPU with CuPy. And then we create data arrays with Xarray. But you see, we supply as input the arrays that we have just created. And then we use this .data structure for the data array that we have created by passing the GPU array. And then you see we make this check here that makes sure that the array on the GPU and the one that you have created with the .data are actually the same. So there was this check here. Check that our GPU and CuPy array are the same with CuPy, and then that gave us a true. And then we are checking the interoperability with NumPy. So you see there's one more question. check that the R GPU and CuPy array are the same also with NumPy, and the answer is also true. And then yeah, we omit some code here, and then at the very end we are doing the device manager to just print what device we're working on. So you see here it's showing a CUDA device, as we said, and then it's device 2. So this example actually, if you just allocate one GPU, it's not gonna work because you see here we are setting device to 2. So if you have just one GPU, the device will have ID 0. So if you get a failure there, that's because of that. Okay, so this is the last slide. With some additional resources, there's documentation for CuPy that shows a speed comparison between CuPy and NumPy, which is something that I mentioned already and that Igor was in a way doing these in his examples. So I suggest you check that part of the documentation. There's also an interesting example of of the usage of CuPy Xarray in a real world case. So this is most likely what folks that work on climate will be most interested about. And we noticed that you may have to modify the data read in this way here to include the compat override and minimal chords. Yeah, so there's finally one more performance comparison, and that is it. Thank you.
Okay, we had one question in the QA in Discord. Actually, two. I answered the first one and the second one.
Let me take a look. So I wonder if I'm looking at the right place. We're looking at Francois' question, right?
So we have two
Oh,
questions.
oh yeah.
CuPy path is where to install the packages.
Slide 10.
So
oh yeah,
that's our installation script, yeah.
Yeah, so if you look into the system where CuPy is installed, that's the path. That's just the installation path. And is there an environment available to time the heap kernels?
So I answered from the AI Assistant. That would be a good one to try in the Open Web UI later today. And I don't know if all of these are valid or if there's some hallucinations in them.
Yeah, normally you would use heap events for timing kernels. And I wonder if maybe you could use the heap Python interface for that and include that in your CuPy code.
Right. The AI came up with some I had not heard of, so it'd be interesting. It could be they're just not real.
In a few words, what's the advantage of using Python heap or CuPy over PyOpenCL, which can target GPU, CPU, NVIDIA, AMD, and Apple?
That's a good question. I think they're interoperable and they both work.
Yeah, I guess. Yeah, the only thing that comes to mind right now it's whether there's maybe like some sub cases where something's not implemented in PyOpenCL that is implemented in CuPy or heap Python or vice versa. I don't have a better answer at the moment.
Yeah, and PyOpenCL may have an opaque data handle. The Python interface to OpenCL is actually pretty nice, but it tend to have opaque handles. So I don't know. It'd be interesting to add that to our discussions. We do OpenCL is not the highest priority support right now, even though it runs on the AMD GPUs. It's just not as active right now. And I think all of them are portable now because, hip Python, you can do CUDA Python, CuPy, you could build that with the CUDA backend. So we're getting portability now that wasn't there even a couple of years ago.
Yeah, and with Python, there's a lot of freedom, probably too much freedom sometimes. It adds questions about what is the best approach, and I don't know if there's a one answer to that question.
Yeah.
Yeah, so someone asked about the exercises, so I think they should be in the exercise document, but if you can't find them,
they are.
Just go in the repo. Yeah.
I'm going to share something else. There was a question earlier that I think is interesting. And so if we go to the Python package index, and we search, there's 687,000 projects, which is both the strength and the weakness of Python. But if we search for HIP, there's a bunch of things that pop up. Some of them obviously not interesting for us, but there's HIP attention. And so maybe that would be interesting. But you got to look at each one of them. Here's our HIP Python fork.
PyHip interface. Hit Python as CUDA. Wow. You can like spend your entire weekend having fun with all this. I like the A hip.
And hips hack. It sounds like something about, the body hip.
I
Okay.
wonder if there's a package called hip replacement.
Yeah. So, and then that's just assuming that they'll call it hip. Maybe we'll look for Rock'em too. And Rock'em SDK. That may be the interface to the placeholder. That may be a future interface for the profiler software development toolkit. FTLLM Rock'em. Okay, no description. Okay, their standards aren't very high for getting into this list. Onyx runtime,
Off the
TensorFlow.
record.
So there's actually a fair number in here of different packages you might investigate. Of course, a lot of them associated with different AI frameworks.
Yeah, so there's a rightful question about what is the reason device to host transfer is almost comparable in unified and discrete memory system, whereas host to device is fast. Honestly, we don't know. It's kind of opaque in the way it works, and that's actually, I think, just my opinion, kind of like the good way and the bad way of using CuPy is that you don't have to worry about that, but if you want to worry, it's hard to get answers. So in a way, I guess maybe Hip Python is more helpful in this case because it gives you more transparency on the memory copies and how you do that. I don't know, honestly. That's my short answer.
Right, and it is dependent on the allocator you use. If you use new versus HipMalloc, the performance is different. And Giacomo actually has a nice little comparison of all the memory allocators and their performance going one way or the other. But it's if you do a HipMalloc, the data is on the device, so that's going to be faster. And it varies depending on if you are doing your first access to the array, maybe loading it into cache, the page table, and the second one, it may already be there, so it varies. It's a little hard to pin down the actual time. And even on the MI300A, you have to populate the cache, so it's not a zero cost. It's just faster than if you had to do it on a discrete GPU. And often people will go back and add explicit memory transfers later because they'll get slightly better performance. If they do discrete, because you can choose where to do it instead of doing it when you hit the page faults.
We also have a question on Magma. Is there any interface to Magma from the Python Rock'em interface? I don't know.
I don't know either.
Let's see if we can find something.
You want to see if that's probably going to be in Hip Python. You want to see if Dominic can answer that?
Let me ask, yeah.
We may not get that today, but we'll post it when we get the answer. And these are always good questions because if there isn't, they may be motivated to add it, or at least the documentation for it. Now, I would imagine that the same thing they're doing to wrap the other Rock'em calls or Rock'em library calls, they could do that for Magma.
So Jose made me realize that there's a little inconsistency in the agenda because we have a break at 3 for 30 minutes, but then the next talk starts at 3:15. So I wonder if we should maybe break now until 3:15 so that Jose can start his presentation at the prescribed time.
Yeah. Let's start that presentation at 3:15, and so exercises and break until 3:15.
Does that work, Marie? Okay. So 30-minute break now, and we come back at 3:15 for Jose's talk on MPI for Pi.
And meanwhile, you all have homework to try all those profiling options and come back with what works or what's.
Okay, see you in a little bit.
Okay, time for coffee.
Okay, I think it's time to get back at it.
Hi, everyone.
Right.
Hey, Jose.
Okay.
Yeah, so we're at time to start, and we know that we cannot cut Jose short, so we're going to give him the full 3:15 start time to 4 o'clock to talk about these two packages. So with that, Jose, take it away.
Yes, so hi, everyone. Here we'll talk about AI application inter-process communications. So let's say that you have an AI application that you want to run. So the AI application and the dataset, your initial dataset, sit on a disk. And from there, you launch your applications. So from the time you launch it until the end of the execution, your application will go through different phases. And the first one is the data pre-processing phase, where data are loaded from disk to memory and transformed on CPU. And during that phase, we have different kinds of steps. First, we have a dataset discovering step, where your dataset or your database structure is discovered. You have information like length, type, and things like that. Followed by the sampler distribution, where you have an index shuffling and distribution. And then we have the data loading step itself, where data are gathered per batch, loaded, and transformed. Also, batches are processed ahead of time on CPU during that phase. And when you complete this step, you will see that a data transfer between CPU and GPU, but technically should be mostly from CPU to GPU, because initial data, they load a lot. You load a lot from memory to GPU, especially when you start doing your training or your inference. Only few data are loaded back, but most of the time it will be from CPU to GPU. And the next step is the data processing phase, where you have data distribution running in parallel, and that is the place where the training happens. So during while going through this step, you are stressing different hardware resources. So here the CPU is in charge of all these steps, and then you have the bus between CPU and GPU that is involved here heavily, and here we have the GPUs. Okay, so you can tell me that, okay, I can use one process to do this, one process to do this as well. That is fine, but it is time consuming. And when you think about reducing data processing time and data pre-processing and processing time, then you will need communication library. And mostly what happens is that you have MPI for inter-CPU communications, and you have recall for AMD inter-GPU communications. So here we talk about reducing data pre-processing and processing time, but the full optimization, when you think about the full optimization, it requires additional tuning that are not listed on the slide. So when I say additional tuning, for example, we can think about memory pinning to speed up the data transfer. We can think about balancing workload per process and things like that. So there are many parameters that we can take into account during the full optimization phase that analysis here. And also, when we think about multi-processes, processes that communicate with each other by sending messages via the interconnect network. And finally, communication are managed by libraries such as MPI, MPI for Pi, we call on AMD GPUs. So let's talk about MPI4Pi. What is MPI4Pi? MPI4Pi, in fact, is a MPI binding for the Python programming language that allow any Python program to exploit multiprocessors or cores. Multiple nodes, it can be between multi-nodes, or it can be between multi-GPUs, it can be between multi-core, things like that. So it is built on top of MPI. MPI, as you know, is a standard and portable message passing system designed to function a wide variety of parallel computers. So the MPI4Pi sends data directly from one GPU to another one by using GPU-aware MPI. So MPI4Pi cannot work by himself. It depends on something else, another basic MPI that is working under the hood. And also, the MPI4Pi can be configured to use any MPI implementation. Where do you get MPI4Pi? You can go to follow this link to get the MPI4Pi. So there are simple ways to install MPI4Pi using pre-built wheels, for instance. But here we leverage, in fact, a GPU-aware installation of MPI, which is done using a script we'll talk about in the next slides. So here, we'll use this to install the GitHub that we have here to install MPI4Pi from source. So you can get it. This is you have a script to install MPI4Pi from source. It's available here. So the installation needs an existing MPI installation, as we said, and the existing MPI installation need to be specified. In fact, we need to be specified in the variable environment MPI path. So here we can use OpenMPI GPU-aware MPI that is presented. You can do module show OpenMPI to see if it is available on the system. So to install this, you have to load. You depend on ROCm, it depends on MPI module as well. You load this module, you get the MPI4Pi, and then you set up different kind of some parameters. You need the MPI-CC, MPI-C++. You need library directories, and then you need to set up the compiler CCMD Clang. So here we are building MPI. We are building directly. Here we are using the wheels, and you have a pip install command line with the directly MPI4Pi wheels that you can play with. So that way you combine everything, the MPI4Pi plus the OpenMPI GPU-aware MPI in order to successfully install MPI4Pi and use it in the context of multiprocessing. MPI4Pi and OpenMPI, you can see that, okay, we have same primitive, same directive. You have all reduce here that is available to reduce all. And in OpenMPI, you have the equivalent that is MPI all reduce. Here you are doing the broadcasting data from one process to all other process, and the equivalent is here as well. And here we are sending data. You can send and receive, and you have MPI send as well. So one important thing to keep in mind is that you can see that we have a capital A. Everything starts with capital A, but you also have everything that starts with all lowercase, that has all lowercases. So you can use all lowercase method, in fact, for generate Python objects, like a command.send, and you can also use method with uppercase letter for buffer-like object. So when you have something related to a buffer, you can use anything that starts with uppercase letter. So for GPU-aware MPI and MPI4Pi, one thing to keep in mind is the MPI4Pi is built again that GPU-aware MPI implementation that you chose. And in that context, the GPU arrays can be passed to uppercase methods. So as we said here, when it is about buffer-like objects, you can use method with uppercase letters to do that. So it is possible to do it especially when you can be passed to uppercase method, as long as they have either TPL package device methods or CUDA array interface attributes. And only C and Fortran contiguous array are supported. Also, we have the buffer that you will need to specify. The GPU buffer must be fully ready before any MPI routines. And as you know, this is in fact to avoid race condition. It happens sometimes, but maybe if you don't pay attention, you can continue having it. So we need to make sure that okay, the GPU buffer is fully ready before any MPI routine operates. So here we have an example of using all reduce and bcast. So we have this is a test where you initialize the communication, we have a set the number of rank. Already we have a rank 0, the process number 0 that is in charge of doing the all reduce. So we have the send buffer here that return the CuPy range, return an array with evenly spaced value within a given interval. And we have a receive buffer, and this buffer has the same shape and data type as the buffer that is specified here. So the same buffer. And then from there, we have the synchronize. The synchronize, you know, the MPI for Pi does not have the synchronize attribute by himself. So we are doing this via the CUDA get current stream, which is in charge of synchronizing before calling the all reduce. So the process 0 initiates the all reduce, and then before we move to the broadcast part, we have to make sure that okay, this we close the CuPy all. We have to test CuPy all close first before moving to the next part. So here, what happened is that it returns true if the two arrays are element-wise equally within a certain range, of course. Now, for the next piece of code, we have a broadcast where the process 0 is again start broadcasting, and we use the CuPy here. The data type, the buffer is a buff. The data type is a complex 64. That is an alias for NumPy complex 64, which is a float complex. And so we have a rank 0 that initiates the buffer like this, and then we have a synchronize again before the broadcast happen. So the principle here between the all reduce and the broadcast that we are sharing here is basically the same thing, and you can see that in both examples. The synchronization is happen at CuPy level before calling the command all reduce or command bcast. Another example is the direct send and receive. Here, for example, that we have, and we have a combination of MPI for Pi and CuPy again here, the same thing. The process 0 that initiates the send to over process. So we define a buffer that is a float 64. We wait until everything is available, and then we start sending the message. And over process, after sending over process, we receive the message. Wait, also we have a buffer, they wait until they receive, and then they start receiving the message again. So all over process, the rest of the process will receive the same message, while the process 0 only sent the message. So this is an example of send and receive. And you can test this on the system that we have, and while making sure that, okay, you check the MPI for Pi module is available, you check if CuPy is available, and then here, for example, we are using 4 processes to run it. Now, how do you verify that MPI for Pi and CuPy run on the GPU? As you hear from over talk Bob and Giacomo talk, they talk about this variable AMD log level. So this variable, in fact, enable heap log on different levels. So you have the level can start from 0, 1, 2, 3, 4, things like that. And when you use AMD log level equal 3, in fact, you enable log on error, warning, and information on all these levels. So when you set up export equal 3, you can set up export equal 3 before running your command line. And once you run it, you will see what is going on at heap level. So basically, you see the heap RTC that create a program and start running it. You have a reduce, you have the postmark, you have all defined different kind of macro. So you will know what is going on in the backend of your program when you run. You set up this export AMD log level equal 3. We have additional resources that are available, and you can also go to directly on the follow this link to see different kind of MPI presentation that are related to C, Fortran, and Python. So basically, we have both available resource available for both HPC and AI applications. So we talk about MPI for Pi, and the other library that is really important, especially on MDGPU, is Recall. Recall stands for Requiem Collective Communication Library. It is an open-hosted initiative library that enables collective communication executed via GPUs. So as people may think about it is like a NICOL, it is a fork from NICOL, by the way, and maintain identical API. So you can just do a drop-in replacement without any problem. The recall is also used for direct send and receive operation. And it supports collective algorithm across multi-processes or nodes. So when you think about running a multi GPU, even you are on a single node, recall is your friend. Now, if you want to scale out and run a multiple nodes, you can also use recall for that. And the communication, as we said, the entire GPU communication, it happens via the network. And here. So we have various primitive or collective ready on via recall. You can do all reduce, you can do all getter, reduce, broadcast, and all other collective primitive that you used to use on MPI are available. The initial support for direct GPU send and receive operation can be done. And this is used in the backend for collective communication for any AI applications. And when we talk about AI application, we need to think about deep learning framework like PyTorch and other framework that we talk about in previous talk. So recall is behind all these deep learning framework that we use. So you have a set of tests that are available. So the typical use of recall are mainly for AI workloads, no HPC workload, and in the context of distributed training and inference. If you remember, during our introduction to this talk, if I go back quickly, we talk here. So if we go back here, we're talking about distributed data parallel. So this is the part where you will basically need all these tools to be operational in order to get to accelerate your code execution and get a great speed up out of it. So typical use, as we said, AI workload, no HPC workload, and distributed training and inferences. The recall is provided as library, and it is not a standalone executable. So we have a different kind of tests that exist that you can access and play with that to see the performance, what is going on, how it works, and the performance you can get out of this. So performance benchmark can be done via recall text, and which is a fork of NICOL test. The recall today is integrated in many machine learning frameworks, as we talk about, such as PyTorch, JAX, and you can control the behavior via environment variable. So recall has different kinds of environment variables that you can access, and we can share that with you if you want more information on it. Here we have a recall test. So this is an example of recall test run on MI300A. You can declose the test. You can after git cloning it, you can build it. It will generate different kind of executable for you. So in the build directory, you will see all the available executable, and this is an example of running this. So here, for example, we are running for here you have a message size from 4 mega to 128 mega message. The multiplication factor between sizes are here. So you can see that, okay, we have F. The multiplication factor is 2, and that's why you can see on this screenshot that you have a multiple of 2 all the time. And we are running on 4 GPUs. So basically, if you look at using devices, you can see rank 0, 1, 2, 3, and 4. So 0 operate on device 0, 1 operate on device 1, and so on and so forth. So basically what happened is that we have one process per device. So like MPI, we have a different kind of collective that we talk about. So for this, we have, for example, point-to-point collective, data send and receive, collective support by Recall. We have one-to-many collective, broadcast, scatter, reduce, scatters. We also have many-to-many collective, all getters, all reduce, all-to-all V, and reduce scatter, and all are supported by Recall today. So it should not be a big problem. It will work out of the box, whether when you start running your application, your distributed application on the GPUs. So as you know, there is nothing new here. It has been, even it is on MPI side, you have all these available. In case of send and receive, so GPU 0 want to send the data to GPU 1. So here we have 4 that will be sent, that will be shared with GPU 1, and that is what we'll get afterward. So before we have the state, and afterward you have the 4 share GPU 1 receive data from GPU 0. The broadcast, so GPU 4 GPU 0 has the data and want to send to all of these GPU available. So we have 4 here. You will see all this share with all the rest of the GPU. So GPU 1, 2, 3 will have these numbers. They will receive all these numbers after the broadcast happen. Next, we have data where each GPU has data that GPU 0 want to receive. The GPU 0 is here, and all these GPU 1, they has GPU 1, 1, GPU 2 has 2, and GPU 3 has 3, and GPU 0 want to receive this data. So what happened is GPU 0 went before the getter, that is the state that we have, the status we have. But after this, we have 0 here at GPU 0. First, the GPU 0 holds 0 at the beginning, and then after the getters, GPU 0 receive data from all over GPUs. That is why we have 1, 2, 3 afterwards. Next, we have a reduction problem here. So before the reduction, we have GPU 0 has 0 over GPUs has 1, 2, and 3. And each GPU has data that GPU 0 want to receive. An element-wise using a sum as a reduction. So basically, that is what we have at the end. GPU 0 receive a summation of the data from each GPUs. So 1 plus 2 plus 3. So these are standard. In fact, it operates the way you used to see on API, basically. Another example is the scatter. The GPU 0 want to distribute element across all GPUs. So we have 0 to 3 data. And we have 3 GPUs available. We have GPU 0 who holds all this data. And after the scatter, we have 1, 2, and 3 available on all over GPUs. The rest of the GPU will receive these informations. And here, similar example, all getters. So each GPU has data that it wants to send to all of us. That is the case of all getters. So before we have the status, but after the all getters, that is what we have at every GPU level. So each GPU receives a copy of the data from all GPUs. So GPU 0 will receive a copy of 1, 2, and 3, and vice versa. You have the same thing happen for all of the GPUs just because we are using all getters. And all reduce, each GPU has data to contribute to reduction here as well. So we have 0, so we have 1, 2, 3, and the reduction happen at each level. All GPUs get the reduction numbers. That is why we have 6 everywhere. Reduce scatters, each GPU has data to contribute to reduction as well. So this is the status we have before And after the reduced scatter, we have each GPU receive a portion of reduction output, depending on the data that you have initially. And then we have all-to-all, all-to-V communication that starts from here, where each GPU has a different message to send to other GPUs. That is the initial state. So pairwise sending between all GPUs. So depending on the case, so before we have this situation and after using all-to-all or all-to-V, we have this each GPU, in fact, receive data from all other GPUs. So all these primitives are available, whether it is not new, we have all this available on a standard MPI, and then we have this available even when you are doing different kind of operation on GPU, sending data via different devices will require this kind of primitive, this kind of collective to be called and executed in order to share data between devices, even on a single node or in multi-node context. So that is what I have to share with you guys today. So thank you. If you have any question, I'm happy to take it.
We have a good question here in the QA channel on Discord. Does communication between two GCDs in the same GPU require RCCL? And I'm going to pop up a diagram of the MI300A to help with this because it's complicated.
Yes, please go ahead and share that.
Yeah, let me see if I can find here we go, Adobe Acrobat. Okay, so, where did it, that's not the one I wanted. Let's see if I can get this other one. Just a second, okay, so this is the diagram of the MI300A. And what I want to be careful of, this is what we have on the Perry-Peak air-cooled. There are 4 MI300As.
Bob, sorry, I think you're not sharing.
I'm sorry. There we go. Is that better? Yeah. I hate it. The screen minimizes, so I can't see what's happening. So this is the diagram of a Perry-Peak air-cooled, Perry-Peak node with 4 MI300As on the system. So basically you've got 4 sockets, each with an MI300A. And what makes this question complicated is that there's 6 GCDs in each of these MI300As. So the communication in the configuration we have here is between those MI300A GPUs, which appear as a GPU to you, but they're really 6 GCDs. And correct me if I've got this wrong, Jose, because it gets complicated. We can also configure each of these MI300As in what we call CPX mode, where we expose the GCDs as individual GPUs. And so then you would be communicating between those GCDs with your communication. So that's why it gets complicated. We can also shard the arrays in Slurm and tell the system that even though it looks like we only have one MI300A, treat it like 2, but divide the memory between the 2 of them. And so that's a different way to partition it out so it appears to be more than one GPU. So when you say, what is RCCL communicating between? It's communicating between the virtual GPUs that appear to you. Is that correct?
Yes, that is correct.
That's why that's a very complicated question. We have been experimenting with CPX mode. That MI300A was originally only a SPX mode, which is a single partition. There is a blog post on CPX partitioning mode that was put out recently that might be interesting if you're going to try out this, different partitionings. And I don't know, Jose, did you talk about RCCL and MPI are actually interchangeable?
What was the question, please?
So RCCL and MPI are interchangeable. You can actually use both in a single application.
Oh, yes. Especially the thing is that when it depends on the application you have and how your application is, you build the application. If you look at this picture, I'm sharing my screen again. Okay, so if you look at this, for example, you see, you can have both depending on how the application is designed. The record technically is in charge of the GPU parts. If you have both, the record will work only on the GPU parts. But if your application has a certain part where the initialization of things like that happen on CPU part, MPI will do that job for you. So you can have both in the same application without any problem.
And if you have GPU aware MPI, you can also mix them.
You can also mix them, exact. Yeah.
And some applications do that because the RCCL can be more efficient for the collectives.
Yes.
Send receive. I do not think they're as performant.
Yes, that's true. And that is why I took some time to explain. Keep that picture in mind. Basically, whatever application, AI application you have, the behavior will be what you are seeing on this picture. You will have a processing phase, you will have data transfer and you will have pre-processing phase, data transfer, and then processing where training happen. And at different level, if you are on a CPU, basically the communication library, the specialized communication library that will be involved will be the MPI part. And if you are on a GPU, then you will see recall or MPI for Pi or NICOL for if you are an NVIDIA system or things like that. They help each other basically. Any other question?
Yeah, there's a question in the chat. Is this CPX mode a kernel OS level setting or a user level runtime setting?
See, that one, you can set that at user level. If you look at our ROCm SMI, we have what can I say, an option that allow user to set up this to set the partition he want to use. So you can do that the user can do that if the system is the admin give the authorization to the user to do it. But otherwise, it is something that is enabled by default in the ROCm package. You don't have to reboot the system as well when you do something like that. You do that when you start, at launch time, when you plan to launch your application, you can set up that mode, the mode that is well suited to your application. If it is CPS mode, if it is whatever partition you want, it can be 2, 4, or 8.
And just to add to the complexity, there's not just compute partitioning, but there's also memory partitioning into multiple NUMA regions.
Yes.
That has to be done at boot time.
Yes.
And okay, exploding head, I agree.
Yes. In fact, when we talk about GPU partitioning, as Bob said, we have two parts. We have the CPU part, we have the compute partitioning, compute unit partitioning, and we have memory partitioning. The compute unit partitioning can be done on the fly when you are running your stuff without rebooting the system. But the memory partitioning will require you to reboot the system to do that at boost level.
Okay, so just to make it a little less scary, a lot of these modes are really for virtualization on the cloud. If you get an MI300 on the cloud, they're going to partition it up, at least in some of the instances, so that there's multiple MI300 X systems appearing to you so that they can get better utilization. In the HPC world, it's a little different, and you can get a little boost in bandwidth if you go to CPX mode, but there's also some other tricks you can do to get better bandwidth in SPX, the single partition mode. So it gets complicated, and I think this is also the discussion about it's complicated for the memory transfers between the unified shared memory memory transfer cost, and then you add affinity and the different partitioning modes, and it becomes a rabbit hole I don't advise you to go down too deep.
Yes. So to give you some example of what Bob said, look, let's say that you are playing with a tiny llama or thing like that, AI application that does not need the whole GPU memory.
We lost you, Jose. Oh no, never mind. I lost you.
Got you.
Oh, okay. So to add a little bit of example, real life example to what Bob said, let's say that, okay, you have some tiny llama or tiny AI application that you want to run. If you have a tiny llama, you don't need to use the full GPU. You can partition that and use, what can I say, run multiple tiny llama at the same time to saturate all your resources. You can do that. And that is one, what can I say, one context where you see the benefit of partitioning your GPUs. Another benefit that you can see, another use case is that, for example, let's say that, okay, here on this call, if you look at, we have institutions here, we also have universities, people or things like that here. If you have students, let's say you have students, for example, and you want to teach them how to program on AMD GPU or things like that. You can divide the GPU by 8 or by 4 or things like that, depending on the number of students you have. If it is just to teach them how to play with GPUs, then the partitioning become your best friends.
Yeah, and we have thought about taking our SH5 nodes, which have one MI300A, make them look like 4, but that would mean that instead of it would divide the memory for each of those GPUs by 4. Well, that might be just fine for compiling or for a front end type of node, but not for production runs where I'm running large models. And so you could have different partitions, Slurm partitions. Okay, we're getting too many partitions here. We could have Slurm partitions, which were designed, like Jose was saying, for students to compile and test things, and then have other Slurm partitions with a lot of memory. And these GPUs are extremely powerful, so that might get you more effective use of the GPUs without, having everybody grabbing a full GPU and then going and listening to some presentation and not using them. Okay, so now that we have totally confused everybody, let's try some of the exercises. Again, you can jump to that, the MPI for Pi and the RCCL examples. There's not a lot in that section. You might also try, so we have built the MPI for Pi using GPU-aware MPI. If you download the wheel for MPI for Pi, you're not going to get that optimization. Do you want to talk a little bit more about the build, what we built with Giacomo?
For MPI for Pi?
Yeah.
Yeah, let me maybe share my screen with the script. Okay, hold on a second. Okay. Okay, so at this repo here that you have heard of so many times already, we have a script to build MPI. So it's this one here. It sits on com scripts and then openMPI_setup. And this is built with UCC and UCX as well for improved collective communications. But let me just go down to the config line for openMPI. Sorry, this is a bit of a long script. Yeah, so this is the line with which we configure MPI. See that we're supplying the with Broadcom flag where we include the ROCm path. So that's how we make MPI ROCm aware, basically, so that when we pass our arrays allocated on the GPU, then it's gonna be GPU aware. And once we have this installed, then we have another script that sits in extras that
Should be in COM. It's in COM.
sorry, it is.
Yeah.
Makes more sense. So yeah, in the same directory, there's one for MPI for Pi, where basically you see we provide this option to supply a module to load when you install, and the one that we load by default is the one that basically sets all the necessary environment variables for that MPI installation that I just showed. That's GPU aware MPI. And then basically there's this step here that puts the MPI path for that GPU aware MPI installation into the MPI config for MPI for Pi. And that's how you leverage that installation in your MPI for Pi. And by the way, I should say something about the blogs. So I'm assuming most of you have already played with the web UI, with the models and the RAG. So in case you haven't noticed, if you do the, actually, sorry, let me grab the screen again. If you're on the web UI, and we said yesterday that if you do the pound, you can select a specific knowledge. So that SPX CPX blog should be in one of these knowledges for the ROCm blogs. So you see that I created 4 different knowledges, and each of these for the ROCm blogs have all the blogs that are online as of, I think, last week. And let's see. So I think it's maybe, actually, let's include them. Oh, sorry. I I always make the mistake of hitting Control pound instead of Shift pound. So let me get all the knowledges for the blogs, and you can ask about that partitioning mode here. So we can, well, I mean, we're already using, we can even try with different models, say Llama 3.2, and ask, tell me details about SPX and CPX partitioning for MI300X in the PUs. And this should actually find that in the source, in the sources, and point you to that. So all this long-winded discussion to tell you that all the ROCm blogs materials are in the knowledge base for the RAG. And something that is, I think, interesting to mention is that if I was gonna just download them from the internet, like select the print option and turn them into PDFs, unfortunately, a lot of text was cut. Like they have certain code snippets that have that scrolling bar that if you set them as PDFs, that goes to goes in the trash. So I basically just uploaded the readmes from our repo so that nothing would get cut. So you have that option here. And I'm hoping that the source, yeah, so the source is this readme that you can actually visualize. And oh, actually it picked up a different blog. So I don't know if I got that one in. I think I did, because it's all of them, but it picked up a different blog where apparently they still talk about the partitioning. But yeah, you've got all the blogs in the knowledge base, so you can leverage that with the RAG. See, in SPX mode, each physical GPU is viewed as a single entity. CPX,
Okay,
Okay.
Giacomo, we have another question in here, which the person asking the question got his own answer from the AI. Our job is done. We can leave.
Which question is it in the chat or in
It's in the Discord.
is there a simple check for verifying GPU or MPI installation? Oh wow. Nice. Good. Yeah, let me run that. I'm curious now.
Yeah, it's you know, we remember that somewhere they said how to do this, and it's difficult to remember where, what presentation. So this capability of searching for it through AI is actually really helpful, even for us.
So okay, so yeah, it's interesting because let me check one thing real quick. Sorry. Yeah, actually, if I run that without loading the module, so here I have not loaded any modules, and there is an MPI installed already. Sorry. So if I run that here with the system one, it shows CUDA. And then if I load ours, it shows ROCm as well. I don't know why the system one shows CUDA, but yeah, that's interesting. Normally I check that to verify my configure my configure options here. So with the OMPI info, you can see how it's been built. And in fact, if anyone is interested in spying how we built that, you can see exactly how with this one. And we have two MPI in the system actually that we have built. The other one is one that's been built with the Fortran drop, which is this. So that MPI is this one here. So if you load that one, so notice, first of all, notice that in the one without the AMD Flank compiler, we built everything with the GCC suite. If now we load the other MPI and run that same command, then you see that we have used the AMD Flank compiler for the Fortran compiler, because the Fortran modules need to be built with that compiler if you're gonna be using the Fortran compiler for your app with OpenMPI. So yeah, thanks. I didn't didn't think of that option to check the MPI extensions as well. So the LLM is already proving to be a success, including it.
And I think you're starting to see there's small optimizations you can do in your installation, at least with some of the packages that may get you better performance. It may require installing from source. It may require, like PyTorch, you may have to reload Torch with the ROCm extensions. But paying attention to the details can help with performance. Okay, we've got about 5 minutes for the rest of the exercises, and then the long-awaited presentation on the AMD AI Assistant creation and how that got put together, so that you might try doing that on your local workstation GPU or on your local cluster. Okay, so 5 minutes, and Giacomo will rest his voice again for a few minutes.
I'm gonna do some voice warm-up exercises in the meantime. Let me answer a question about MPI for Pi real quick before we move on. So Gaurav, you had a question. So let me show you what I did. So I just allocated a node. So one node, one GPU, but then I also included this for the processes. And then if you just run it like that, as you were trying to do, it should work fine. So if you don't see the GPU, if it says no heap capable device, it means that you don't have a GPU. So maybe you were running this from the login node. So make sure that you do an salloc so that you get the GPU. And to make sure that you did get the GPU, run a ROCm SMI. So if you run the ROCm SMI, you'll see that there's the GPU here available, and then you can see what that is by doing ROCm info grab mi, and it'll tell you which one. Okay, so if you don't see the GPU, do the salloc, and also when you do the salloc, you also need to say how many GPUs you want. If you just do salloc -n1, then you're not gonna get the GPU. And also, folks, remember, so if you do sinfo, it'll tell you what you have available in terms of nodes. And if you do sq, you'll see what's the utilization. And notice that most of you folks are on the PPAC nodes. So for instance, there's 3 nodes that are unutilized, the SH5, 15, 33, and 36. So if you just need a GPU, I recommend going there since no one's using them. I'll hop off this one in a second. Remember that the default partition is the PPAC. So if you do the salloc without specifying the -- partition like I did here, you see, you will be put in the queue for the peri-peak nodes. So if those are all taken, then you'll have to wait. But if you specify the partition, so if you do here, if you do -- partition and then specify this, then you can get one of the SH5 nodes that are available. So keep that in mind, okay? So let me hop off the node so y'all can get it. Okay, so I think it's time for the last talk of the day. Yeah, 4:20. So Bob, should I start?
Yeah, go ahead. Let's dive into it.
Oh, sorry.
Somewhere in there. One of these presentations. Pick one.
There it is. Okay. All right. So we have all familiarized yesterday and today with the Open Web UI and the AMD AI Assistant that we have created for this event. And by the way, we'd be very interested in learning whether you found it useful. Hopefully you did. We want to know how you used it, what issues you found, if you have any recommendation or advice on how to make it better for the next events that we'll do. This was the first time that we did it, and I was very excited about it. I hope that you found it useful as well, but please let us know in any way. You can just let us know on Discord or send us an email or LinkedIn, whatever you want, not the chat because that goes away. But we'd be very, very interested in hearing how, how that worked out for you. Okay. So yeah, so in this presentation, we'll focus on 2 ways you can build this model for you to use. And we already talked about why we want to use it. We want to use it to get the most up-to-date information on AMD GPU software and some about the architecture as well. We've talked about MPI, so you might be wondering how to get information on the Numba domains, how to get information on the links between GPUs, and that's something that hopefully you were able to get querying the LLM, and that's certainly something that we were hoping you would be able to get. So the questions you could ask can be somewhat simple, just about like, hey, how do I make sure that my PyTorch workload runs on AMD GPUs? Or you could dive deeper and ask about the partition, the memory or compute partition that we've we've seen right now. And I did just check, and that blog is indeed as part of the knowledge base. And in fact, I posted a screenshot on Discord where I asked that same question, but instead of asking it to Llama 3.2 and then using the pound for the knowledge base, I just asked it directly to the AI assistant. And that was a lot more complete. And also I checked that in the sources, one was the README associated with that blog post. So all is good. Okay, so now the question is, I'll show you two ways to set this up, and to decide which way is going to be best for your scenario, you have to wonder how many users you're expecting in your system. For instance, the reason why we opted for the open web UI is because we had about 114 people expected for this workshop. So the other one that I'll show you, it would not be suitable in this case. Do you allow containers to run in your system? Because in the web UI that we're using relies on Podman to execute. And also there's the question on whether or not you can do basically the forwarding of the web user interface in your system. Okay, so let's start from the very beginning. So we will be using something that's called RAG. To create this model. RAG stands for Retrieval Augmented Generation, and basically it consists of augmenting an existing model with additional data so that you can basically leverage that data when you have the model give you its answers. And the reason for that is because, as all of us, I'm sure, have seen, pre-trained models sometimes tend to hallucinate. Basically, that just means that they will give you some bogus answers. And the problem is that, these models are most of the times created in a way that they convey their answers and communicate to you in a very confident way. So you might very well think that, the answers that they're giving you is correct or it's pertinent, when in actually just they kind of just made it up to give you some answer. Okay. And the idea of using RAG is to actually prevent situations like this with a dedicated external database. And the important thing about this RAG approach is that you actually do not need to retrain the model. You just use one that's already pre-trained and add to it this external database. So yeah, just to kind of compare side by side what you would have if you wanted to choose a traditional generative model, let's say, or a RAG. So as we already said, the traditional model may hallucinate, and that is fixed with RAG. Fixed. I mean, it's improved with RAG by providing external data that's very much on point and accurate. If you need to update the knowledge with RAG, you just put more or replace the data. For instance, during this event, I have been updating the slides as they were changed in the knowledge base. Whereas with the generative traditional model, you need to do training again. And something that's good about RAG that you've seen already is that it actually cites the sources from the external database. So not only you can see exactly what's used to provide the answer, but in case the answer maybe is not super satisfactory to you, you can look at the source directly, and maybe by reading the source, you're like, oh well, now it makes a lot more sense. It happened to me that I had to do that. Something else that's not to be discounted is that to get a lot of accuracy with the standard models, I've seen, and I'm sure most of us had as well, that you need to get models that are big, that have a lot of parameters to make sure that the answer you get is actually a good one. But with RAG, you actually can pick a smaller model, provided that your knowledge base is accurate and big. So you can compensate using a smaller model with a larger external database. And here we are comparing, again, the RAG with a few different approaches. So we talked about prompt engineering, which is probably the simplest that you can do. And you see it doesn't use any external knowledge or model modification. You're basically just working out your prompts to get the most out of the model. It's fast because there's basically nothing you have to do, and then you don't need to train. But it at the same time, since it's so simple and fast, it's actually not gonna give you a lot in terms of gains. Then there's the fine tuning, which needs model modifications, since you'll basically be doing some more training again. And therefore, for that reason, it will be compute intensive. And the cost is also high because you need to do more training. So with RAG, you don't in general need any training. We're not doing any training in our case. And you don't need to modify the model because, as you've seen yesterday, you just use a base model. And so RAG, in a way, it can be seen as somewhat in between prompt engineering and fine tuning in terms of complexity and benefits. So if you want more details on how RAG works, you can check out their paper here that's cited in this slide. And we're not gonna spend time talking about the nitty-gritty stuff about RAG. But if you're interested in learning more, there's sources that are available to you. Okay, so for all of this workflow that I'll show you, we're gonna be using Ollama, that I'm sure you've already heard about even from us yesterday. So in the spirit of being a real AI champion, I just asked ChatGPT what Ollama is. And it told me that Ollama is a company that provides an API for interacting with large language models. So basically, we'll be using Ollama to pool the models and then run them so that we can interact with them, in short. You can install Ollama with a script that they provide. You just need to specify your operating system, basically. And installing it is actually pretty fast and simple. And you can even do it on your CPU laptop if you want. Just be aware that it's gonna run pretty slow if you pick a big model, and also downloading the models would be slow. So the Ollama application will be installed in your user local directory. In particular, the executable will be into the bin. So once you have installed, if you want to make sure that it's working and it's there, you just do a which Ollama, and you should see this path here, user local bin, displayed in your terminal. Or you can even do an Ollama -- version, and it'll tell you what Ollama version you have. And so the good thing about Ollama is that it's really easy to shop for models. You just need to go up on this website and then look at what models they have available. And if you click on one specifically, it'll tell you also the size and the sizes actually that you have available. So for Llama 3.3, you just have 70 billions. And if you don't specify the size and you just select the latest, then this table here tells you which one is the latest. In this case, it's the 70 billion, since there's only that one. And then this command up here tells you how to run it. So let me see one thing. Yeah, okay. So that command there tells you how to run it. And it's interesting because the models here are free. So you don't, you just install Ollama and then copy paste this command after you've done something else that I'll tell you. And then it just works. And the interesting thing is that these all run locally. They don't run on the internet. So you shouldn't have any worry about information leakage. They just run locally on your machine. So for what concerns Ollama support of AMD GPUs as of August 27 of this year, you see that there's this table here that covers the consumer GPUs, the workstations, and then the data center GPUs, the AMD Instinct, which are the ones that we have for this event. And the 300 series is also mentioned there. We have checked that it works pretty well, in fact, on the MI210, which is part of the MI200 series. And to start up Ollama, you have to start the Ollama daemon by just doing Ollama serve. And then I suggest you also include the ampersand so that it runs in the background. And you might have to export also the Ollama host environment variable in case you are getting errors such as that the address is already in use. In that case, you would just increase by 1 the last digit here. And in fact, if you're running Ollama locally just to play with it, then you don't have to worry that much about what you set this Ollama host to, but I'll show you that for the purpose of the web UI, it's actually very important what you set that to, or at least you have to remember what you set that to. So once you do the Ollama serve, you see that here you get lines that look like this that say AMD GPU is supported. And you'll notice that it works because it will go pretty fast. And in case it goes very slow, then something is off. And that is actually the case for the MI300A GPU. Remember that in the table here, they say that they support it. However, there's actually this issue that last time I checked is still open that instead mentions the fact that in practice, they do not support MI300A because it doesn't work, unfortunately, as of today. And in fact, you see it says unsupported Radeon iGPU. And that is the reason why for this event, we have two clusters, the AAC6 that has all 300A, and then we have just one MI300X node to run Ollama. In fact, on the 300X, Ollama works. And you can see that it's going pretty fast. So once you have done the Ollama serve, you can do Ollama pull to pull the models that you're interested in. So for instance, for this event, we've pulled Llama 3.3 70 billion, Llama 3.2, and Gemma 3. So when you pull them, basically you are downloading them and making them available to you whenever you want to use them. And if you do Ollama run and then the model name, it will pull them first and then run them locally on your terminal. Okay, so going down to what are actually the two ways of doing RAG that we are exploring here. So there's the Open Web UI that you are already familiar with, this is best suited for situations where there's a lot of users accessing the system. And that is because in this way, you have Ollama run only on one specific node. And then basically users take advantage of that through the web UI. Plus, you get that nice web UI interface. And with that, it comes a lot of advantage in terms of how you actually supply the knowledge base for the rag, because you can just drag and drop PDFs or MD files. You can upload directly a directory to the website, so that's really nice. And as you've seen, you know, the issues with that is that you have to handle getting the SSH tunnel to work. So there might be some hiccups there. And also the supported way is through containers. So if you have a system that does not allow containers for some reasons, then you can't do that. And there is a Python option available in the Open Web UI docs, but we haven't tested it, and they say it's not the official supported way. So you know already about this option. The other option that we haven't shown you yet is just by using a Python script with a command line interaction for the LLM. So no fancy user interface, good old terminal to interact with. And the pros of that is that it's really easy to set up. You just you know, run the Python script basically, and you don't have to rely on containers. No need to worry about making sure that the port forwarding with Ollama works, because that can be pretty tricky. But obviously, the issue with that is that every time you run it, you need to run an Ollama instance. So if we enable this option for this event, all of you would have had to download the models with Ollama and run them on your terminal, which would have made everything chaotic, and we would have run out of space, I'm afraid, pretty quickly. So that's not the right option when you have multiple users on a system. But nevertheless, we're going to show it to you, because, you know, when you get home, maybe you have a workstation GPU, and this option is actually going to be pretty useful for you. And I'll show you exactly why in a second. So there's two ways you can do it, or I'm sure there's actually multiple ways, but we're showing you two in this case. So we could you could do it with Conda if you like it. So, you know, you have to install Conda, but in our systems, we have a module for that. So we're doing the module load Conda. Just make sure you have Conda in your path. And then you are gonna create a virtual environment. You're gonna clone our exercises repo, get into the subdirectory called ML examples, and then reg_langchain demo. And you're gonna have to install a bunch of Python requirements. Beware, those are a lot of Python packages, a lot of requirements. So that's gonna take a second to download. Or you can do it without Conda, just by basically setting yourself a path, a directory path, where you're gonna be installing the dependencies. So here I just created this directory called AI Assistant deps. And then I'm doing pip install with the requirements, and then doing my favorite thing of supplying the -- target and then pointing to that directory. And since we're not in a Conda environment, then the next thing I'm doing is I'm putting that dependencies directory into my Python path, so that whenever I do an import in Python, all those dependencies will be visible. Okay, so the next thing to do is to start up Ollama and pull the model. So this example here relies on Llama 3 70 billion. So what you do is you do an Ollama serve. So you locally start up Ollama. You may have to set the Ollama host environment variable if you get that error that I showed you before. Then you can pull the model that this code relies on. And then you will run this Python code that's called AMD AI Assistant.py. So the way to run it, well, first of all, you could just run it with --help and it will tell you how to run it. But the way to run it is by specifying the raw conversion that you're targeting and also whether or not you want to force scraping. So the way this script works is it's going to go online and scrape the web for certain documents, which will create the knowledge base that it's going to rely on. So the reason why you specify the raw conversion is because the code is built in a way, you see here in the screenshot, that it's going to go and scrape the official documentation. So by specifying the raw conversion, you're telling the code what documentation you want to scrape. And the -- scrape is gonna force the scraping. This is because once you've done with the scraping, the code works in a way that it's gonna save locally that knowledge base. So the next time you run the script, you're not gonna have to do the scraping again. You'll be able to directly interact with the LLM without having to wait, because the scraping can take a long time, especially if you do a lot of recursions. So the -- scrape will force rescraping if you've already done it once. Giving you more details about this scraping process, so you can specify this max depth environment variable. Well, not environment variable, variable for the script, this value, that decides basically the recursion of the scraping. So for instance, if it's set to 1, then you see here on the right, we have hard-coded the pages that we want the code to scrape. And if it's set to 1, then it will also scrape the links at this page, these pages that you have included. If you set it to 2, we'll scrape the links of the links, and so on. So you can tell that it may take a long time if you have that max depth be large. And also there's the risk that if it's too large, then you're just gonna go scrape some irrelevant content. So you have to be a little mindful of that. But you see, we have hard-coded the web pages that we wanted to scrape. So there's the documentation, there's all the blogs, and there's a lot of other stuff. And you can just edit this, include whatever you want, remove. This is where you actually go and act on what type of knowledge base will be included. So see, once the scraping is done, it'll tell you how many documents it had scraped. And then it's creating the database on your disk. So the next time you run it, if you don't include the -- scrape, then it's not gonna scrape again. And basically you'll get the prompt immediately. So that's gonna save you quite a bit of time. And you can see that similar to what you had with the Open Web UI, whenever you ask a question, it'll also show you the source. So the question that I asked here was, how can I optimize PyTorch to run on AMD GPUs? And as source, it picked up this this blog. Actually, no, sorry, it's a page in the documentation that's called Inference and Optimization from the ROCm for AI subdirectory. And this is how the answer will look like. So everything is from terminal. So, if you wanna send it a code snippet, say to explain, for instance, you're gonna have to paste it in the prompt of your terminal. So this is easy to set up, easy to interact with. And I think it's an additional tool that's good to have in case you weren't available of this option. Okay, so next up is to give you more details on how we set up the one that you're currently using with the Open Web UI. And as we said before in the previous slides, it can be pretty tricky, especially you have to be careful to make sure that the Open Web UI sees Olama, because in my experience, a classic issue that you get is that you hop on the web UI and then you click on select models and there's no models. So that means that Olama running on your host system is not seen by the container where the Open Web UI is running. So you have to make sure that you have them talk properly. And one way that we have found is working for us is depicted here. So basically you would SSH onto your host system first. In our case, well, it used to be AAC 6, but now it's GPU 60, where there's the MI300X. So you don't need to do step 2 there, since there's only one node, and that's the login node. And then we had to add this line to the .olama/config.yaml file to make sure that Olama would listen broadly. And then we had to export the Olama host variable in this way. So 0000 colon and then the port number that we want. So for instance, it could be this one here. Then you run the Olama daemon on the background. You pull the model, and then here is the step where you need containers. So in GPU 60 we used Podman, so we pulled the image for Open Web UI, and we pulled the one that has Olama as the default interface. So see, there's the colon Olama that you'll need to pull. And the next tricky bit is to have the proper podman run command be executed to launch this, to execute the image, basically. So there's some port forwarding magic here that you need to do. And then very crucial is to specify the correct Olama base URL. So we found that this option for the Olama base URL worked, but actually what we're using now with GPU 60 is an option where here, instead of using HTTP host containers internal, we just have the IP address of the GPU that we're running on. So make sure that you query the IP address from terminal and then set it into this variable. So you would do Olama base URL HTTP. Sorry, no, without the HTTP. So it would be Olama base URL equals the IP address column and then the port number. And that needs to be the same one that you had supplied into the Olama host. So there's this matching that you need to do to make sure that the communication happens between the host where Olama runs and the Open Web UI container. And then, then the other flags are pretty self-explanatory. And then the last 2 steps are to run the tunnel from your local machine into the web UI, and then you just need to open up localhost 3000 on your browser. So you see why this is a little fidgety, because you need to make sure that all the little things match so that the communication can happen. And there's a couple of things you can do to troubleshoot issues. So the first basic thing you can do is just kill Olama. I mean, you'll need sudo for that, but you can just kill all the processes that have Olama serve somewhere in their name. And if you get issues with Podman, you should also stop and remove the container. Be very careful with removing the volume, because the volume is the one that contains all your data for the Open Web UI. So for instance, all your accounts as users will be in the volume, all the knowledge base. So if you remove that, you lose everything. So be very careful with removing the volume. Oh, sorry. In general, unless you want to remove the volume, so you want to start fresh, maybe like you created an account as admin and then you forgot the password. In that case, you'll have to remove the volume. But if you don't need to or don't want to, then in general, it's just enough to stop and remove the container. If you get errors such as 505 internal error when trying to access localhost, sometimes it's just enough to refresh the page. Okay, so once everything works, you'll see on the localhost a graphics that looks like this about Open Web UI. You know, there'll be there will be very motivating graphics like astronauts and very cool stuff. And then you click on get started and you'll have to create an account as admin. So as I said a couple minutes ago, make sure you don't forget the password, because if you do, then I think there are ways to reset it, but they're a little cumbersome, and you know, it's very possible that you might end up having to delete the volume and start over, but that will make you lose everything you've done there. So remember the password. And once you have your admin account, you can go ahead and click on the admin panel and then add users. So that's actually what I did with you all to get you on it. So here, for instance, there's an example where I created an account for Bob and then I made him an admin. You just have to click here on the plus, and then this panel down here will show up. You just type the name, email, password that you want to give them, the role, and then you save, and there you have it. And actually, for you all, I created a CSV file. So basically, I uploaded it as a table, and then there it was. So for what concerns adding the model for RAG, you'll have to go on Workspace and then create the knowledge. So here you click on knowledge and you click on plus, and then you can describe what knowledge you're interested in creating. For instance, you know, I created one about profilers, rockandblogs-AI. You make it public so that anyone that is a user can see it. And then you can click on this plus where you can select how you want to add that knowledge, either as a file or directly a folder. You can even drag and drop, and then you had that. So for what concerns actually creating the model, instead of clicking on knowledge, you'll have to click on models. And the first thing to do is you'll have to select the base model that your RAG will be built upon. So in this slide here, I selected Llama 3.2 because at the time we were trying to make it work on AAC 6. That was unfortunately only running on CPU. So I was trying to select a smaller model, but now that we have GPU 60 with 300X, then I could select Gemma 3 27 billion. So you select the base model, you make the visibility private if you want, or public. For us, it's public. And then you can also set a prompt that kind of sets the tone about what this model will intend to do. Remember, yesterday we talked about this. We are somehow creating a little persona for this model, and here I told the web UI that this is supposed to be an expert GPU programmer with knowledge of AMD GPU software and programming. And then down here you select the knowledge, and then you save it, and here it comes, and it's here. So there's actually a little more that you can do to tune it a little bit. So this is tuned in a way, not a lot, but we made sure to try and somehow make it more performant in the way that it would read the documents that we provide. And that is done by acting on some parameters that are called the top K sampling and the top P sampling. So basically the top K selects the top K most likely tokens from the model's predicted distribution. And the top P selects from tokens whose cumulative probability doesn't exceed the value P. So what does it mean in practice for us? So it says it here. So basically, higher values of the top K will increase the creativity of the model. So you can get a wider range of responses, and the lower values will make it more similar in the way it responds. And the top P is about being a little bit more conservative in the way it responds. Another parameter to take into account is the temperature, which regulates the probability variability. This is not a technical term, but it describes how often your answers will vary. So let me just be more specific. So say that you set the temperature to 0, then you can expect that for the same prompt, the answer you get will also be the same. And as you increase the value of the temperature, then you'll get more variability, because you have to remember that these LLMs answer in a probabilistic way. So in general, the same question will not give you the same answer. But if you set the temperature to 0, then yes, you can expect to get the same answers for the same prompt. And you can go ahead and click on advanced parameters when you create the RAG model, and you can go and edit these here. So in our case, we have the top K set to 40, top P to 0.95, temperature to 0.4, and then the maximum number of tokens to 1,000. Max number of tokens is the number of tokens that the model can generate in the output. There's also this note on the Open Web UI docs that say that if you're using Ollama, you should increase the context length to 8,192, so that the context length is bigger, and therefore the model can basically not get lost as it is parsing the knowledge base that you supplied. And you can actually also set this as an environment variable when you run Ollama. There's an Ollama underscore context underscore length that you can set to this when you do the Ollama serve. Something else that's relevant for this is the chunking for the text, which is basically the way that the input data is broken up, so that when you analyze it, you have set it up in these chunks, and therefore you see larger chunks preserve context but may include irrelevant information, and smaller chunks have precise retrieval but may lose the relationships. So in general, between 256 and 1024 tokens per chunk is a good balance. And you can select the chunk size if you go on the admin panel, click on settings, and then documents. This will decide what way for the document parsing you want to use for the Open Web UI. So you select the chunk size here that we had set to 1,000, and then you can select the top K here as well. I don't know exactly if this one that you select here and the other one are different. I don't know exactly what happens. I know which one gets priority, but just in case I set them both to 40. And then here you see there's the reg template that basically tells the model how to behave when you interact with it. And there's already a default that you can modify if you want. Let me just point you to this line that says, if you don't know the answer, clearly state that. And I also added this additional sentence that said, do not make up an answer if you don't know it. So we want to reduce hallucination to the minimum. And then always remember to hit save, because I have forgotten that a couple of times. And then you have it. You've seen that already it's providing you the sources, and you can click on the source and it will show you the document. You can even select multiple models here and ask the same question to all these models at the same time. And so you can compare each answer that you get. And actually, there's even, if you click up here on the top right corner where there are these levers here, if you click there, you will be able to modify through the web UI the model parameters, such as, once again, the top K and the top P. So again, if you select our model, the AI assistant, and then change these parameters here from the filters option, I can't tell you which one is picked, if it's the one that I set or this ones that you set up here override it. I'm not sure. I recommend you test it out on your own if you want to. So that is it. Thank you for sticking around with this presentation and the whole day presentations. I'm sorry it went 7 minutes over. I just had too much fun with it. So yeah, so Bob had to drop for another meeting, so it's we don't have to wait for him. So I'm just gonna give it back to Seema and the team for the final closing arguments.
Thank you very much, Giacomo. And also, I would like to thank all the AMD team, Bob and Jose as well, for this deep dive in advanced Python tool. And this wraps up our session today. And thank you all for joining us. And we are looking forward to seeing you tomorrow for our third day. And I would like to tell you, have a good morning, evening, and afternoon to all of you. Thank you very much for joining us, and see you tomorrow.
Thanks, everyone. See you tomorrow.
Thank you, everyone.
Thank you.